Hey everyone. Basically, I can't make it tomorrow because I need to meet my own group for project 2. But I'm just gonna give you a little rundown of my predictive model that I did. So basically, what we're doing is predicting power outages and the chances there will be a power outage based on all these different predictors based on the original data set that we're given. So let me just walk you all through it really quickly. This is basically just importing all the packages that I need. And then me loading the data, all the normalized values from the original data set. You can see all the columns here. And then pre-processing, basically, from years 1972 to 1999, there was no power outage data, so I'm gonna get rid of that. This is what it's doing right here. And yeah. So check for null values. Essentially, what this is doing is seeing if there are any values with empty cells. If we do, we get rid of them. However, there are no null values in this data frame, so we are good. Now here are kind of the meat and potatoes of this. So predicting power outages, what we're gonna do is create a model. So first we're gonna assign y, which is our dependent variable, to the outages count column. And then for x, we're gonna assign the different predictors for this. There's reasons why I got rid of these columns and I don't want them in the model. It's because year, month, we already have the year and month columns. There's no point of having it combined in the same way. That's gonna lead to multi-collinearity, which is what we do not want. Outages count, we don't want that because that's the dependent variable. Northern total daily sunspots and southern total daily sunspots. We're getting rid of those. Basically, banned into the analysis. They are basically the same when it comes to they're basically the same. Also, total daily sunspots we are going to keep. So if you have 3 that have nearly like the same output, it's going to skew our model a lot. So yeah, we do not want that at all. So that's why we're going to get rid of it. And they're also very specific. We don't want our model to be very specific. We want it to be in between specific and not specific. And this is to prevent overfitting and make our model stronger. So data partitioning, we're going to split our data set into training and validation data sets. Basically, the training data is what the model processes first. And you give the training data, it practices and understands this training data. After that, after it's trained, we're going to give a new data set, which is the validation data set. And it's going to process that, and we're going to compare both to see how accurate the model was in predicting both data sets. Train model, we're training the model, creating it, putting the training data inside of it. Now we're gonna look at the accuracy of the model. As you can see from right here, here are the columns that we kept for our predictor variables. Look at the p-values right here. Month has a very high p-value. P-value should be usually below 0.05, at most 0.1. But this is 0.698. This means that it's not statistically significant. This means that there's a high chance that whatever outcome that it puts out is by chance. It's not based on the data, and that it will most likely not be very accurate. Earthquake 0.983 is terrible. That's nearly 1, which means this it's not going to be accurate at all. Same with magnitude. 0.95 was way too high. So what we want to do is probably get rid of these because it's going to mess up our model, right? And backward elimination right here, this code is doing virtually the same thing. It's just it's a process where it tries to figure out the optimal columns to keep and the models and the columns to get rid of. And oh, wow, look at it right here. It says year and total daily sunspots we keep, and we get rid of U3, which is what we kind of looked at earlier, right? Based on the p-values. Forward selection is the same type of thing. It's looking for the same thing, different process though. However, it is giving us the same result. So it's saying keep year, keep total daily sunspots, get rid of those other columns. That's perfect. Now we kind of have direction of what we want to do. Now we're going to create a new model with different X and Y. So our new x is going to be year and total daily sunspots, right? And we're going to keep the same y. Here's the same thing, partition the data. Now we have our new model right here. Put the training data in, and look, now we have our coefficients. Year is 0.134848, and total data sunspots is about 28, 0.28. So both of them have a positive effect on power outages, and we'll kind of go over that later when I show you guys the chart of the coefficients. But yeah, and these are the regression statistics. Root mean squared error 0.7542, kind of large. Mean absolute error 0.5340. Not too large, right? Because our normalization is pretty much -4 and 4. 0.53 isn't that much of it. That's like what, like 10%, 15% off. So yeah. So now I'm going to create the chart showing the coefficients. So what this is just saying is year has a positive effect, slightly positive effect on power outages. So the later the year, the more likely there is to be a power outage. Total daily sunspots. The more total daily sunspots there are, the more power outages there would be, is what it's saying. So yeah, there's a positive correlation between these variables and power outages. Training data prediction. So we're going to do a prediction model compared to the actual data. So the model is going to give us the prediction, or what it predicts based on those variables, and it's going to give us and compare it to the actual data, right? Here, all the things. Residual is basically predicted minus actual to see how far off the predicted was from the actual data. I created this chart right here. This is perfect though. This is a normal chart displaying the residuals. It's a normal bell curve for the most part. A lot of the data falls under -1 and 1, which means that the data and the prediction is not far off at all. So yeah, very strong prediction, nearly a perfect normal curve. However, that's just for the training data set. Let's try it on new data that the model has never seen before. Let's try it on the validation set. We're gonna do the same thing. And then we're gonna have this residual chart, not as accurate, not as normal. A lot of the data does not really fall near 0, but most of the data does fall between -1 and 1. There are a couple outliers right here, but for the most part, it's fairly accurate. So our prediction model is accurate. So yeah, that's my code. And this is like the meat and potatoes of it. This is just kind of proving, yeah, there is a moderately positive correlation between sunspots. And power outages as well as the year. So maybe there's going to be more sunspots as the years go on. That's why there's more power outages. Some more things to figure out after this. But yeah.